Hi, folks. Today we're going to learn about special products of polynomials. All the problems we see today can be solved using the exact same method we learned in the last section, where you use FOIL, the distributive property, to just multiply two binomials together. However, recognizing these special patterns when you have a special multiplication problem, such as a perfect square trinomial, when you have a plus b the quantity squared, or a minus b the quantity squared. Recognizing that is going to be helpful when we start doing multiplication in reverse, when we start taking a large polynomial and we try to factor it. So that's why it's helpful to start recognizing these special patterns, even though these particular examples could just be done using the distributive property. These multiplications can be done that way. So let's look at some of these special patterns. First of all, 3x plus 4, the quantity squared. Now, whenever we have an addition binomial inside parentheses and we're squaring it, the answer is going to take this form, a squared plus 2ab plus b squared. And so all we need to do is identify the a component. The a comes before the addition sign, and the b component, which comes after the addition sign. And then we plug those values in to this format, a squared plus 2ab plus b squared. So my a is 3x, which I will square, plus 2 times a, which is 3x, times b, which is 4, plus b squared, and my b is 4, so I will square it. So now that I've plugged the a and b values into the format of this perfect square trinomial, then I just simplify. 3x squared, well, the 3 squared is 9, and the x squared is x squared. 2 times 3x times 4, 2 times 4 is 8. 8 times 3 is 24, so that's 24x. And then 4 squared is 16. So this is my final answer following this format. And once you get used to this format, it can actually be faster than kind of thinking first, outer, inner, last using the FOIL method. Let's look at another perfect square trinomial, this time with a subtraction problem. So when we have a subtraction problem in parentheses, the answer takes this format. So we're going to write a squared minus 2ab plus b squared. So again, we have to identify the a value and identify the b value. This time, this is important. I've made a big deal previously about always making sure that negative stays attached to the term that it's in front of. However, for the purposes of this equation, the b term is just what I have inside the box here. It does not include the negative sign. And that's going to be important as we plug it in to this equation. So my a value is 5x, and I've got to square that. Then I'm going to subtract 2 times a, which is 5x, times b, which is 2y, not negative 2y. And then we add b squared, and b is 2y, so 2y, the quantity squared. Now, this negative sign takes care of the fact that there was a negative sign there. That's where it went. It's built into this formula that we're using. The negative sign doesn't need to appear over here at all because a negative number squared ends up being a positive number. So that's why it doesn't appear over there. All right, let's simplify. So 5x squared is 25x squared. 2 times 2 is 4, times another 5 is 20. So it's minus 20xy. And then we square the quantity 2y squared. 2 squared is 4. Y squared is y squared. And this is my final answer for this this perfect square trinomial with a subtraction problem inside parentheses. Please notice that this method worked even when I had two different variables inside parentheses. It didn't matter that I had an x and a y, this method still works. The second pattern you should be able to recognize is a difference of two squares pattern. Difference of two squares. So it's called the difference of two squares because the answer has a square minus another square, a difference of two squares. When you look at this, the problem, when you're asked to multiply it out, you don't see the difference of two squares. You see a plus b times a minus b. Here, t is my a value and 5 is my b value. So that's what you see um, when you're looking at a difference of two squares pattern. We need to write this in the form a squared minus b squared. And again, this negative sign is not part of that b value. My b value is 5, not negative 5. So I'm going to plug these numbers in. A is t, so I'm going to square that. And b is 5, so I'm going to square that. So this final answer from this multiplication problem is t squared minus 25. So you can see this saved us quite a bit of time compared to actually doing the distributive property, being able to recognize this pattern. One thing that I'd like to note is that there is no special way to come up with an answer that says a squared plus b squared. Okay, so don't think that once students learn this answer here, they think that they kind of go back up to this a plus b, the quantity squared, must result in this answer. This never comes from multiplying two binomials together. Let's do one more example of a difference of squares pattern. Here we've got our a value. Here we've got our b value. And so when we put this in the a squared minus b squared format, we've got 3x, the quantity squared, minus y squared. So that's going to give us 9x squared minus y squared. So again, we see from the answer why this is called a difference of two squares pattern. It's less easy to see from the problem, but it's more easy to see from the answer. Again, this is going to be super helpful when we start factoring and we try to find out what factors were multiplied together to give us the polynomial that we see. This strategy can be used for regular math problems, ones that don't involve polynomials, ones that don't involve variables. So for instance, special products patterns can be used to multiply normal numbers together like 26 and 34. For instance, 26 is 4 less than 30 and 34 is 4 more than 30. So I'm going to write this as 30 minus 4, because that's 26, times 30 plus 4, because that's 34. And I see here, if I think of this as being a difference of two squares pattern, I've got my a value and my b value, then I can write this as a squared minus b squared. I can think of this as being 30 squared minus 4 squared. 30 squared is just 900 and 4 squared is 16. So I get the answer 884. So this is something you could do in your head. While I wouldn't try to directly multiply 26 times 34 in my head, I'm not that good at mental arithmetic. I can quite easily do these steps in my head if I have a special pattern to the numbers that I'm multiplying together. Let's look at a real world example of when these special patterns might appear. And I'm actually a biology major, so this one is near and dear to my heart. These are called Punnett squares, and they show how alleles can be inherited from parents. And this isn't biology class, so I won't get into definitions like alleles. I'm just going to use words like genes here. So For these border collies, they can have black patches or brown patches depending on the genes that they carry. Every dog has two color genes, one from each parent. So inherited one from the mom, one from the dad. So this here is going to be the mom of the next generation. But of course, this mom had a mom and a dad, got one gene from each parent. And then here, this is our dad from the next generation, dad for the next generation, but he had a mom and a dad, and he inherited one um, uh, gene from each parent. And so, one more thing you need to know before we move on is that black is dominant over brown. So, if you have one black gene and one brown gene, the black gene wins, and those border collies would have black patches. Um, so, if the offspring are equally likely to inherit either gene from their parent, from each parent, then what is the likelihood that they'll end up with black patches versus brown patches? That's what we're looking at in this question. So we've got a big B, little b dog. It's got one black gene and one brown gene, mating with another big B, little b dog. What percentage of the possible gene combinations result in black patches? Well, we've got it mapped out for you here. If I have big B with big B, this dog is definitely black. If I have big B with little b, that dog is black. It has the brown gene, but the black overpowers the brown. Same thing for this dog here. It inherited one black, one brown gene, and the black wins. Only this dog inherited two brown genes and therefore has the brown patches. So here what we see is how many result in black patches. 3 out of 4 of these gene combinations result in black patches, and 3 out of 4 is 0.75. And to convert that to a percent, we would multiply by 100, so that equals 75%. Now, how can I use a polynomial to model this particular example? This is just like saying the mom has one black plus one brown gene. The dad has one black plus one brown gene. So let's multiply those together and see the possible results that we have in the offspring. And so this is a perfect square. This is going to result in a perfect square trinomial. I'm going to have, I'm going to do, this is like my A value. This is like my B value. So I'm going to have capital B squared plus 2 big B little b plus little b squared. All of these offspring are going to be black. And the only possibility for brown offspring comes from this gene combination here. I hope this helped.